Okay, task 2, option 1, generate AEs in the context of WhiteBox threat model. So in the context of WhiteBox threat model, we will use an ensemble as the target for the attack of the attack. So in this task, we will generate the AEs using the optimization-based approaches. So we support two approaches here. So the first one we will without the EOT. So in this approach, we simply treat the ensemble model as a single model, as we did in the context of zero knowledge model. So we extend this equation in the ATHENA paper. So equation 1 is the loss function for generation of AEs for a single model. So we extend this equation for an ensemble by averaging the losses. Okay, we will, so first you need to configure the attacks. So basically, in this approach, when you are using this approach, you don't have to, you can use the JSON file you used for your task 1. So the Python example will be the same file, and the API will be the same as for task 1. And go to this place to check for the parameters, tunable parameters. So you can see here, the only thing I added is this flag for EOT approach. So basically, you need to pass your target model here in the benign samples and the corresponding labels, true labels, and your configurations. And since for this approach we are not using EOT technique, so you will let this be false. So in this task, this model must be an ensemble model. So that's the only difference for this task. I mean, between this from the task 1. So in task 1, you will pass the undefended model here. That's one model, and here you pass the ensemble here. Okay, so we will prepare for the generation. So we go through each variance. We will get the configurations for this attack, and then call this API to generate the AEs using this attack. It will return you the generated adversarial examples. Then we will evaluate your generated adversarial examples with your target model. So here is the ensemble, right? So you get the predictions and get the label. We will compute the error rate and then we will plot 2 samples, and then we save the generated adversarial examples to the place you specified. Okay, so that's it. The same logic. So here when so in the context of this WhiteBox thread model, we will use this ensemble as the target. So you need to load a pool of weak defenses. So in this example, I will use a tiny pool consists of 3 weak defenses. So you will get the classifiers and then define your ensemble. So in here, I will name it as the target because we will generate the AEs for this one. So you will load the benign samples and the labels as we did in task 1, and then the rest will be the same. Yeah, we will generate for 5 benign samples, and then call the function. Let's start from the very beginning. Okay. So you can see when it's successfully performed, you will see the numbers here. Okay, then run the second one. This one. Okay, then generate the AEs. So load the model. Okay, it's really fast. Okay, so we will load, you can see we load 3 weak defenses here, and then we will create, we will build an ensemble using these 3 weak defenses, and then generate the AEs for this ensemble. So you can see the first adversarial, the first attack we are using is FGSM with epsilon equals 0.2, and we are not using EOT here, so EOT is off. And then the error rate of this 5 sample is 0, so none of these 5 samples can fool the ensemble. And then the second attack we performed here is PGD with epsilon equals 0.3. Still, we are not using EOT here, and generated AEs cannot fool our ensemble model. So the ensemble model I'm talking here is actually the target model of the attack. Okay, so the second approach, so we will turn on this. We will use this EOT tech. We will use this EOT. So for the detail of this EOT, how does it work? How it works? Please refer to this paper. And they also provide source code and some example for this approach, for this algorithm. You can check it here. And then the ATHENA paper, we extend this EOT approach for ensembles, because in the previous paper, this approach was for a single model. Yeah, so the equation 7 in the ATHENA paper was the loss function. We extended for the ensemble. So currently we only support FGSM and PGD as the adversarial optimizer. So basically, that means we only support these two type of attack with EOT. So to launch this type of attack, you need to provide the configuration for your distribution. And you can, so in this case, I config the distribution in the same JSON file. So attack zk mnist JSON. So let's see this one. Okay, here you can see. So this part will be the same. We will add one key value pair here for the distribution. So the key will be distribution, and the value is actually a dictionary. So this dictionary is the configuration for the distribution. We will sample. We will sample some random distributions from some random transformations from this distribution. So it will require the number of the samples you wanted to samples from this distribution. And so this is the size of this set. And the type of the transformation you wanted to use. For example, here I wanted to sample from the rotations. I wanted to sample 1,000 samples, and each of them will be rotate randomly in this range from -45 degrees to 45 degrees. So where can we check the parameters for this distribution? You can go to attacks. So under this attack, you can see a distribution Python file. So in this file, we implement the randomly sampling from these distributions. So go to the bottom, you will see here is the class. It will define the distributions we supported here. So basically, rotation. So randomly rotate the input and adding some random Gaussian noises or translate the images. Or this is shift actually. This is also called shift. So you will shift the images by some offsets, and then some affine transformations. So this random distribution, we will first so here sample from distribution. Basically, you will give an input. This is a single image here, and then the configuration of the some information of the distribution. So if you wanted to sample from random distributions, here we will first select a random distribution from either rotation or Gaussian noises, or translation, or affine transformation, and then we will perform that. We will sample an image from this, from the distribution you choose here. Okay. Yes, so you need to configure your distribution in this JSON file. If you are not using EOT, that's fine. You can just leave it, make it, I mean, so you can assign the value as none, or you can simply remove this key value pair if you are not using. Yeah, so here is an example for the attack with the distribution. Yeah, so in this task, if you are in this task, when generating the AEs using this EOT approach, there are some, you can try to generate several AE variants by tuning these parameters. So basically, whatever you can tune in task 1, you can still tune that parameters for these AEs, for this kind of AEs, and then you can change something. You can try different settings of this distribution. For example, the number of the samples and transformation types, something like that. Yes, so the examples will still in this file, and the APIs to generate the AEs still the same. You can check the tunable parameters for the attack in this file, and the tunable parameters for the distributions, you should check it in this file. Then okay, so here everything will be the same as you are using the normal approach. So basically we will still need to load the pool of these weak defenses, and then create a target ensemble, and load the benign samples and the corresponding true labels. And here, if you are using EOT approach, make this to true. Then when you so you just call the function, and let's run it. So you can see it will load the weak defenses here, and then it will generate AEs for you. You can see it will take it's expensive than the normal approach. So with EOT on, it will take more time. And actually, if you notice this, we are still using FGSN with epsilon equals 0.2, but if we we are using this AOT approach as well, we can generate stronger AEs, right? So here the error rate will be 0.4, will be 40%. Okay, so here the same settings for the attack, but if we are not using EOT, you can see the error rate will be 0. So yeah, so here it's the same. So that's it for the option 1.